Hi, my name is Arwen Bradley, and today I'll be presenting Cinematic-L1 video stabilization with a Log-Homography model. This is joint work with my co-authors Jason Clivington, Joseph Triscari, and Rudolf van der Merwe. We're at Apple, where we have a lot of iPhone videos to stabilize. Here's an example of our stabilization. Notice that the stabilized movie has stationary, panning, and smoothly accelerating motions, similar to what cinematographers shoot with equipment like tripods, dollies, and Steadicams. Our approach is a 2D video stabilization method, which does not handle depth and can suffer from parallax, but is fast and robust. In performance-critical contexts like capture time stabilization, 2D models are often the best and sometimes the only choice. Our method builds on the work of Grundmann et al., who simulate motions achieved with professional camera equipment by formulating a convex optimization problem penalizing the L1 norm of the derivatives of the stabilized path. We extend their model from affinities to homographies by using a log-homography transform to preserve convexity. We formulate new constraints to accurately preserve crop and optionally keep salient objects in frame, and propose a windowing strategy for online processing. Our method runs at 300 frames per second on an iPhone XS. Here's some intuition for L1 stabilization. Tripod stabilization tries to remove all camera motion, but that can fail by cropping down to nothing or introducing distortion when there is too much motion. An alternative is to smooth out the high-frequency shake with a Gaussian kernel, for example, but then you don't get crisp motions like perfect tripod. L1 tries to achieve tripod stabilization and constant velocity pans where possible, linked by smooth accelerations. In this example, tripod stabilization introduces significant crop and distortion, while simple smoothing is always drifting slightly. L1 first pans and then locks onto tripod. Recall that we want tripod, panning, and constant acceleration segments. These motions correspond to 0, first, second, and third derivatives of the stabilized motion, respectively. Hence, we want the first three derivatives of the stabilized path to be sparse. L1 norm minimization is a useful heuristic for encouraging sparsity while maintaining convexity. Following Grundmann, we set up a convex optimization problem to minimize the L1 norms of the derivatives. We also add an L2 term for fidelity to the original path and constraints to enforce crop. Grundmann formulates the problem in terms of affinities, which are linear transforms that handle rotation, translation, scale, and shear, but not perspective. For perspective, you need homographies. Notice the residual perspective wobble with the affine model. Homographies are challenging to use in a convex formulation because they are nonlinear, so we instead work with log-homographies, which are elements of the tangent space of the manifold of homographies. Log-homographies approximately turn composition into addition, so we can formulate L1 stabilization with homographies as a convex problem. Our method can satisfy any crop allowance the user specifies. We can also optionally keep a salient object in frame or centered in the frame. For very shaky videos like this one, the log approximation might raise concerns, but we control the correction magnitude via fidelity and distortion terms to avoid making corrections severe enough to invalidate the approximation. Grundmann et al. Formulate the optimization problem in terms of affinities, then refine the solution with homographies in a residual motion suppression step. The post-processing smooths keystone wobble, but can consume significant additional crop. In contrast, our method solves directly with homographies, so it can rigorously satisfy crop and other constraints. Here, Grundmann's result is based on a 30% crop budget, but actually consumes closer to 40% due to the post-processing, while our method accurately satisfies the crop constraint. One of the biggest limitations of this work is its 2D nature, which means it cannot handle parallax. However, this is essential to its performance, which is critical for real-time on-device applications. Our method runs at 300 frames per second, which is orders of magnitude faster than 3D methods like content-preserving warps. An avenue we'd like to explore in the future is data-driven tuning of the L1 model weights. Thanks so much for listening. For more information, please check out our paper or attend our session.